Okay, well now it's recording. Good thing I caught that. Um, and oh yeah, I need to share my screen. Oh, it's like the biggest, bluest, greenest button. Okay, so um, all right, cool. So I think I'm sharing my screen. Do you see that?
Yep.
Okay, great. So let's just trial the transition. So I'll be like, oh, Amber, this presentation, this background, these announcement. Oh shit. I will not say shit. Oh, here's some announcements. Here's some sponsors, and now let's talk about Amber's background. So I'll leave this up. We'll talk about some get to know you questions, and then I'll say, okay, Amber, can you please share your presentation? I'll stop share, and now go ahead and put yours up.
Is it there?
It is. Are you gonna do the full screen or whatever?
Yeah, sorry. Here we go.
Nice. Okay, that looks good.
Oh, now I stop. If I hit escape, it stops sharing.
No. You're sharing. You're sharing. It's just so that's
Okay.
like the full screen look.
Okay.
Maybe like just can you like tab one? Yeah. So you'll go through your thing. You'll give your presentation. Great. Yep.
Okay.
Nice. And then at the end, you can, I don't know if you have like a question slide you can leave up. You can bring it back to the original slide.
Yeah.
You can whatever. One thing I would just say is like sometimes I don't like it when people will like we're talking for like 15 minutes on questions and they just leave it on like some random like disclaimer slide or something that's weird. So yeah, I would say like this slide or the opener slide or whatever would be good if you're not
I
jumping.
didn't have like a last thank you slide.
That's fine. No, I think this is cool. This will stimulate questions.
Yeah.
So that's
Great.
good. Awesome. So and then yeah, and then at the end, yeah, we'll pretty much be like, okay, bye everybody, and then that'll be it. So
yeah, I'm like, we were adding data yesterday afternoon to this.
oh really? That's
Like
cool.
hot off the spectrometer.
Haha, you should use that phrase. Hey, I'm just gonna refill my water. I will be back in like
Sounds good.
1 minute or less.
Do you guys have about like a week lag time with that podcast?
Say it one more time.
Do you have like a weekish lag time from when you record and then you release the podcast?
It's actually a little longer. So like the one we recorded this morning won't come out for like 6 weeks or something.
Oh, really?
Yeah. So by the time you get on, and so like we're recording every week now. So we record right now, we're recording every week and then we release every other week. So we're like getting more, we're like every time we record, we're pushing it out an extra week basically. So,
Yeah.
and we've got, I think, 2 more recordings before yours, I think, or something. So yours won't come out for like in like 10 weeks or something at this
It'll
point.
be a while. Yeah. Cool.
Yeah. So, but we do everything in a time vacuum, so it's like when it comes out, it still seems kind of like it doesn't age. We kind of do it purposefully to not age. So
like not talk about what's happening this week in the news.
exactly. Well, we do things like recently, or if you
Right.
talk about, or, or you don't say like, January 22nd. You say, early this year, this winter, shit like that. So I like the way this microphone sounds, but it looks awkward as fuck in the thing. Also, I literally just I didn't even have 5 seconds to think about it. I don't know. I just closed
Left
one
it.
Zoom and opened another, and now I'm here. So, just zooming around. Cool. Any other thoughts?
I don't think so. I guess I can stop my screen
yeah.
sharing.
I was about to say stop. Let me go back. So we've got our nice little thing, Amber. Okay, cool. So, all right, when it hits 59, I'll start it so people can come in. The tendency seems to be to just like be awkward and quiet for those 2 minutes, but I'll reiterate, we don't have to be awkward and quiet. We could have a discussion about the weather
Talk about the
or
bush tits that were already at the bird feeder.
I think
That's
right
their real name.
if Bush is gonna be the first thing you say right when we start, I think that would be positive. So all right, cool. So it's 10:59. I'm gonna start it. So keep your
All right.
keep it clean, Amber. Okay, here we go. Welcome everybody. We're just gonna give it a couple minutes to let folks join, and we'll get started about 1 minute after the hour.
Maybe you need like some background music to play so people know that it's working in the future.
We should get that. Yeah. What style would you recommend, Amber?
I don't know. We need to get a CAN member to like create one for us.
I'm sure there's somebody who's like can members, like a DJ or in a band or something, who maybe could do
Yeah.
something for us. Get some can theme music.
Yeah.
I like that. It's a great idea.
I mean, obviously it needs to be reggae genre, but
Okay, that's
just
what I was
kidding.
getting at. No, I'm a big reggae fan. Yeah, that would be great. Let's do that. Welcome everyone who's just coming in. We're gonna give it just another minute to let some folks join before we get started. If you have suggestions for what kind of music we should incorporate in the future, drop us a line. All right, everyone, we're just going to give it, well, actually, there we go. We're at 1 after, so we're going to go ahead and get started. So, welcome everyone to CAN Journal Club. My name is Nigam Aurora. I'm the Publication Committee Chair at CAN, Cannabis Chemistry Subdivision of ACS. We're very happy to have our own Amber Wise, who is in addition to everything else she does, she's also the Programming Chair at the Cannabis Chemistry Subdivision. So, but in her day job, Amber is the lab director of an analytical chemistry lab. So she has a lot of cool stuff to share with us. So, to give a little more background on Amber and her presentation, she'll be speaking today about cannabis vaporizer aerosols, nonpolar methods for collection and analysis of 10 metals. So, a little on Amber's background. She earned her PhD in chemistry from UC Berkeley, followed by a postdoc at UC San Francisco. Before transitioning to the cannabis industry, she was a chemistry professor for 7 years in San Francisco, Bangladesh, as well as Chicago. After leaving academia, she was the scientific director at Avitas Agricultural in Washington and Oregon for 2 years, overseeing the cannabis extraction and refinement facilities and handling data analysis, new product development, scientific growth of the company. Dr. Wise also designed and presented educational seminars for bud tenders and other cannabis industry professionals, and was invited to the Health Ministry of Canada to present on the production of cannabis extracts and concentrates. In November 18, she joined Medicine Creek Analytics, an entity at Puyallup Tribe, as their science director. Medicine Creek is a Washington state certified testing facility for I-502 cannabis products, and was the first cannabis testing lab in the state to also achieve ISO 17025 accreditation. Dr. Wise is the programming committee chair at CAN, as we had just discussed, and she's also serves at the Washington Department of Ecology Cannabis Science Task Force Steering Committee. In her spare time, she also volunteers as a master gardener and enjoys sewing and going outdoors in the Pacific Northwest. I know she's also a big bird watcher. She's avoiding the temptation. She's here with us now instead of watching birds, so we thank you, Amber. So before we get into the presentation, a few can items to share with everyone. Oh, excuse me, I had my presentation in the wrong slide. So, some announcements from Can next month. Tune back in at the end of Feb for a presentation from Can member Jerry King, who is an expert in CO2 extraction and is extremely experienced. I'm looking forward to hosting Jerry next month. Other exciting news, we have several can sessions coming up at the ACS Spring National Meeting, April 4th to 16th. So this is a completely online event, and we have these following topics are going to be addressed. So there's women in cannabis, advancements in cannabis analytical methods, a session for cannabis treatment for specific medical conditions, as well as some presentations on uses of the cannabis plant beyond cannabinoids. And finally, as always, if you're not already a member, make sure to join CAN today to keep up with all the great stuff going on. Before we move on, I'd also like to thank our sponsors, Heidolf North America, Carbon Chemistry, Pure Proven Professional, CFS Consulting, which is actually Jerry King's consulting company, as well as Perkin-Elmer that has your cannabis solutions. So with that, I'd like to ask Amber a few questions. So you guys in the audience can all get to know her a little bit about her background. So Amber, welcome to Can Journal Club.
Thanks for having me, Nigo. It's good to be here.
Absolutely. So you know, Amber, you're a big part of what we do at Can, so it's really fun to have you here, but be able to delve into some of your work on the analytical side. So Amber, can you tell us a little bit about how did you know, what was your journey like going from academia into cannabis? Maybe like you can speak to your motivation or your interest to get into the space.
Yeah, a lot of it was academic burnout and relocating to a legal state, and it kind of just being in the back of my mind as a potential opportunity that wasn't, a university position. But also, once I had a lot of trepidation in the beginning, certainly. This was almost 5 years ago now, and worried that, is this the last job I ever get? Am I ever going to talk to another scientist from my past ever again? And what's been really great and rewarding so far is being part of this really fast growing industry. And, there's all kinds of issues and problems, which is, another topic for another day, but ultimately it's really fascinating. There's a lot of low-hanging fruit in terms of the science to be done and published. I think today's talk is a really good example of that. And there's never a dull moment. There's always something new coming up. And one of the reasons I got into it as well was to lend some legitimacy and raise the scientific bar to the industry. There's so much science behind cannabis, from the growing to the harvesting to the curing to the extractions to the formulations. There's science on every step of the way, and the industry is ahead of the science in most aspects, and so we need to catch up as scientists. So it's like exciting to be kind of contributing to that for sure.
Yeah, no, I love that response. I think it's extremely exciting to be contributing. That's also why I'm here. So,
And it turns out scientists still talk to me.
yeah, you know, actually, what's funny is that I find these days that not only do scientists talk to us, but they think that we are like almost like novel, right? Because we took the leap before. So, and I think there'll be a lot of people to come later. So, I'm curious too. You know, I agree. The topic today is highly, highly interesting, and we'll get into that in a lot of detail shortly. But you rattled off some of the other, you know, areas. I'm curious, like, what else you know, you've worked across so many different things, working in the production side, working in the analytics side, you know, working in the education side. What is, other than the topic of the talk today, what do you see as, you know, the most interesting or promising, or maybe areas that just you're interested in? Can you share a little more about your like thoughts or ambitions just about what's interesting in the space?
Yeah, I I think the educational aspect really needs to solidify a little better. There's a lot of, legal issues with universities jumping on board full bore, just being, federally legal and all of the grant money and issues with that. But, um, obviously things are probably going to change dramatically on a federal level in the next couple of years. So I don't know what the most interesting aspect is, honestly. I mean, I could talk to anybody about almost any aspect for hours sometimes because there's so many interesting things. Um, I think getting some real analytical standards. What I mean by that is lab protocols for analytical testing, quality control testing, quality assurance testing, whatever you want to call it. But the compliance testing varies widely state to state. And if we're going to have some sort of federal program, it's going to be really hard for companies that are in more than one state to figure anything out if they're working under different sets of rules. And so, the policy drives a lot of it, but also the science needs to catch up. And I'll touch on this a little bit in the beginning of the talk, but the inability for academics to still handle cannabis in its actual THC form is held things back. It's uncountable, like how long it's been delayed.
Yeah.
So for better or for worse, there's a lot of opportunities for scientists as soon as they can, find a space where they can handle the dangerous cannabis in its real form.
Yeah, you
The
gotta.
form that people are buying in recreationally legal states and medical states. Um,
I have
and
a. Or sorry, go ahead.
that's all I wanted to say.
Just to add on to what you're saying is that I have a colleague who's a university professor, and his whole thing was that for a while he was buying THC standards. Like you would buy like a tiny amount as like a standard for an HPLC. And then he was like taking the THC out of that to run his experiments because that's
Yeah.
all he could buy before he got while he was waiting on his Schedule One. So, anyways, I think you highlighted a lot of great points, and appreciate you sharing, your kind of journey and some of your thoughts before we hop in. So, speaking of hopping in, I'm gonna go ahead and stop my share. Amber, can you go ahead and get your presentation up?
All right. How's that look?
All right. It looks good. If you take us to the full screen.
Is that going?
Awesome. Yeah, that looks great. Okay, Amber,
Okay.
we'll hand off the mic to you and excited to hear your presentation.
All right. Well, thanks, Nigam, for the introduction. Thanks, everybody, for joining. I got to say, I'm a little nervous today, more than normal for some reason, but part of it, I think, is we were adding data to this literally yesterday. So this is like hot off the spectrometer. Some of this data is really, really brand new for this week. So a really brief introduction about the lab. So Medicine Creek Analytics is a standard compliance testing lab for legal cannabis in Washington State. It's kind of our bread and butter, our client samples, for legal sale here in Washington. We do a lot of R&D, research and development testing for folks. Pesticides and heavy metals aren't required for sale in Washington State, but we do have the capability for both of those. So a lot of our business includes companies that are interested in screening for these contaminants. We are owned by the Puyallup tribe of Indians, and this photo I have here of what the Westerners call Mount Rainier, the native peoples called Tacoma, Tahoma, and this is the international phonetic spelling for that. And this is out the window of the lab, actually. Unphotoshopped, just cropped out I-5, that's all below there. It's not very photogenic, but we're very lucky to live in such a beautiful place and really lucky to have the support of the tribe for this. The ability for them to invest in really high quality instruments and high quality staff, which is sort of the next thing I want to acknowledge, is the two guys who really helped me out on this. They did all of the lab work and analysis, Charlie and Dr. Srini Malampati. Wouldn't be here without them. So want to acknowledge their contributions here. And just a general overview of this, all of the data that I'm talking here, we're actually splitting up into two different publications. And so the first one has been just submitted a few weeks ago. still in review. So that will be more on the kind of newer collection methods and method validation. And then the second paper will be a little bit more of the actual cartridge testing aerosol data. So this is just on the bottom here, a little bit of a overview of, metals being in the vapor potentially. This is an image of our setup, and I'll go over that. And then we do some microwave digestion, which is how you prep samples for heavy metals analysis in our ICP-MS. So moving on, I do want to just kind of acknowledge a few terminology issues, or not issues, just clarifications. There's obviously scientific definitions for aerosols, gases, and vapors. And I just want to acknowledge that I do know what the difference is. And we end up using the term aerosol and vapor really interchangeably here because we haven't characterized this vapor really at all. We know that there are some liquid oil droplet particles. We know there are some gas phase molecules. There's probably some water vapor potentially, but we have not characterized these. I'm not sure anyone actually has. And so I'll be using aerosol and vapor a little bit interchangeably to, represent the stuff that you inhale. And if we think about gases and aerosols in cannabis, if you're thinking about something like smoking a joint, that's a combustion process. You can get particulate matter, tar, those kinds of things, cannabinoid oil droplets, we're not even really sure. And there can be gas molecules as well, vaporized terpenes, degradation products, combustion side products, all kinds of different things in that mixture of smoke. And then if you think about something like a non-combustion process, this is a dab rig of, just using a heated surface to heat up the oil or concentrate that you're using. Those can also result in both a mixture of aerosols and gas phase molecules. So I just kind of want to clarify that here. And then also, I try to use the word concentrate mainly, but it's easy to just refer to oil as well. But really what that is just the extract, the concentrate, the oil that goes into the cartridge. And I'm not talking about tincture oils or anything like that. Okay, so I'm going to jump right into the experimental design a little bit and how we developed the collection process. This slide is showing kind of a traditional way of collecting gas phase particles for cigarette analysis. There's often a filter paper. So this would be where the cigarette is here at A, smoking device. There's a filter paper in the stream of aerosol to collect the particle fraction of that mixture. And then the gas phase would theoretically go through the filter and into liquid-filled impingers. There's usually 2 of those to make sure that all of the gases have the ability to dissolve in that liquid. And then there's some sort of suction on the other end. And so we took that layout, and here's an actual image of our setup here. We have this is our battery device here, and I'll talk about that a little bit more in a second. This is the actual cartridge attached here. This is the tubing. We bought a CH Technologies smoke machine, and that actually creates the suction part and the different puffs. And so the smoke travels from the cartridge, and here are 2 liquid impingers. This is a nice photo that shows an actual during a puff session. So this is a little cloudy because there's actually aerosol vapor mixture in there, and the impingers are bubbling here down at the bottom. So the gas phases travel through both these impingers, and then the smoke box is what's causing the draw on the puff there. Really quick, we did actually investigate. I'm not going to show any data for this, but you'll notice that there's no filter here after I just mentioned that it's standard to have a filter in the beginning of the process. We did a number of studies where we incorporated a filter as part of this, and for a couple of different reasons. One being we weren't really able to find filter papers that didn't have a lot of background in the metals that we were trying to analyze for, and the background was also really inconsistent. So we couldn't just necessarily take one sample and subtract them. The other reason was it created another additional sample prep step where you have to physically digest the whole filter paper and analyze it separately. And we did actually look at with and without filter paper, and we didn't really collect many more metals with it. So we just got rid of it for simplicity's sake and time conservation. So we don't have a filter paper collection part of our process. One of the other things, talk a little bit about the puff profile. So there are Caresta and ISO puff parameters that are generally used for standardized cigarette and e-cigarette analysis. And so our experiments are generally 50 puffs, and that's a bit of an arbitrary number, but also we dialed it in a little bit. So that was a good number to consume a reasonable amount of oil so we could get a measurable signal out the other end after we did dilutions and things. And we have 3-second puffs with 42 seconds of rest between them. And that's kind of our biggest difference here between the Caresta and ISO methods. They have a 30-second rest, and we increased it a little bit so the vapor had a chance to really dissolve in the liquid properly before it went into the so it was all dissolved in the liquid properly. We take 25 puffs and then take a 10-minute rest and then take 25 more. And a little bit of reasoning for that is some of the matrix oil that we made, the model matrix, was really thick. And when you take 25 puffs, sometimes it takes a little bit of time to sort of seep down back into the bottom of the cartridge. So it was really just a way to give the system a little bit of a rest, give the battery a bit of a cool down, the heating element a bit of a cool down. I'm not aware of anybody who takes 50 puffs in a few minutes off of a vape cart. So anyway, then the volume per, the volume rate, sort of the rate of puffing is 25 mils a second. So we have about 75 mils for our puff size. And for Caresta and ISO, they have a maximum of 55 milliliters for a puff size. So a little bit differences there, but generally pretty comparable, I think. And the other thing to mention here is, and we'll talk about all the logistic complications more near the end, but we bought an adjustable voltage battery, and we were noticing that, it was relatively high quality. It wasn't the cheapest one we could find. Even with the relatively high quality battery, we were seeing really inconsistent voltages, puff after puff. So we had to leave the battery plugged into the wall for all of our experiments to maintain consistent voltage for each puff. Then one other small detail is this instrument has an automated button pusher. So during experiments, this cartridge is actually facing the other way, and there's a little pneumatic thing that pushes the button, so it's really consistent for each experiment. Okay, so really quickly, I'll just kind of chat about the method validation that we did on this collection method. Am I missing a slide here? I don't see that slide. So I have, okay. Oh, this is the slide I wanted to talk about next. Okay, well, we'll talk about the method validation first. Once we collect the samples, there's solvents in the impingers, and I'll talk about the different solvent impingers in a minute. I thought that was the next slide. But we have the impinger solvents. If there's aqueous liquids in them, we dilute those to an appropriate acid content and directly inject those for ICP-MS. Some of the impingers we ended up using organic solvents in. I'll chat about that in a minute. Those, we dried down the organic solvent, so there's just residue left, and then digested that and analyzed normally in the ICP-MS. And anything else that I talk about analyzing, we analyzed some cartridge bits, we analyzed oil, we analyzed some flour, we did end up analyzing some filter paper. Those were all about 0.2 to ½ gram samples digested in an Anton Par microwave digester. So this lower picture on the right is kind of the inside guts, and this is just a picture of the device itself. The digestion acid mixture was generally 5 mils of concentrated nitric acid, 1 mil of HCl, and 5 mils of water. And it's about an hour plus digestion method I didn't show here. But essentially, we got good linearity for our calibration curves. We got good recovery for our lab control samples, and good recovery for our matrix spikes as well. There's a bit of a high recovery here for manganese. The manganese was seen because it's in really high levels in flour material naturally. And so even in the concentrate, it's a little bit higher. So the matrix, when you spike a matrix of oil with a known amount, you're going to get a little bit more than 100%. And our LODs and LOQs, these are actually just recently updated. We had some higher values for some first round of experiments. We haven't changed the method at all, but we were calculating our LOD and LOQ off of 5 ppb spikes or 5 ppb standards, and we've recently updated that to much lower concentrations, and so we have some lower LODs and LOQs as well. So we have some good detection limits, and these are the units on these LODs and LOQs are ppm, and that is basically a ppm back calculated to the sample itself that would get digested. So ppm in oil or ppm in flour or something like that. Okay, I'm just like checking my notes here to make sure I'm not skipping anything. All right, so one of the hurdles we had to overcome, like before we even started the experiments, was how are we going to spike the oil with a known concentration of metals so we understand what our recovery is. You know, ideally, no concentrate really has any detectable levels of metals, and so how are we going to know if we're able to see them or not? So obviously the big hurdle here is cannabis concentrates are highly nonpolar, very viscous, and metal standards all come in water. So how do we mix those together? So we investigated a couple of different solvents, but ultimately we decided on isopropyl alcohol. And we basically, because isopropyl is miscible with both water and cannabis concentrates. And so we take a small amount of the cannabis concentrates and dissolve that in some warm IPA, about 45 Celsius, just so it's all nice and warm and dissolved. And then spike in 10 ppm final concentration of our aqueous metal standards. And you mix that up really well, and the whole thing is a very miscible and, you know, homogeneous solution. And so then we just remove those solvents with a rotary evaporator with some vacuum, and resulting in, you know, a viscous concentrate with known levels of metals. And I'll chat about the levels in a minute. And then we also did some experiments with flour combustion, and so we did have to also spike flour, and that was pretty straightforward. You just grind it up, add your standards with a little extra water, mix it all together and air dry it for a day, day and a half, and you get a really nice dry flour that you're able to combust. So getting into a little bit of actual data here, I didn't put error bars on this, but these error bars are actually much smaller than the error bars you'll see in the rest of the graphs. But the background levels of metals, so these are just the matrix that we created. Oh, I forgot to mention, this is kind of an important aspect. The reason we're able to have real cannabis is partly because we are, well, 100% because we are a tribe. And this lab is on tribal land. And the tribe has a compact with Washington State that allows us to have a cannabis research license. Washington State has a cannabis research license option, and the tribes have a separate compact. And so that's one of the awesome reasons why we can actually have real cannabis. And so the matrix, the model matrix that we created initially was made from leftover client samples. So it was a mixture of CO2 concentrate, distillate, you know, some various samples. So it wasn't just one type of concentrate. And so we had to write a little bit of a research proposal to the state and let them know, the Liquor and Cannabis Board, so they're aware of this research project and where the cannabis is coming from for this project. So in case you're wondering about the legality of this, we don't have a DEA license. We have tribal status and a research license under Washington State. So the background levels of metals that we found in our model matrix, so the brownish bars are the concentrate and the green bars are the flour. And so we have this axis is ppm. So in the concentrate, very low levels overall of these metals, background levels, and a couple of these, copper and manganese, are found naturally in flour. You'll see these are off the scale, so 149 ppm of manganese in flour, and that number is really, really variable between samples as well. The error bar on that is much larger. And so just to give you a sense for what was present in the unspiked material and then after spiking, so our target concentration for spiking was 10 ppm. So we got really nice recovery, about 75, 85% for all of the concentrate. Mercury is a little bit low, but considering we used vacuum and a little bit of heat to remove the excess solvent, mercury is the most volatile, so it makes sense that we might have lost some of the mercury in the rotovap sample prep step itself. And then the flour, the spike recoveries looked pretty good as well. And again, obviously we have higher levels for these ones that are naturally occurring. So they're already above 10 to start with. All right, so this is a slide that I kind of put out of order. But now that we have some model matrices to actually put into the system, we needed to optimize our collection methods. And what we're looking at here this is the fritted glass insert for the impinger. So this is the tubing that the gas actually comes down, and these are fritted glass. And so the gas, this creates really, really small bubbles in the impinger liquid, which helps the gases dissolve properly. So these images are when we use the standard acidic aqueous liquid, which is what is normally used for metals collection in our impinger, the oil droplets and aerosol mixture were just making it really brown, clogging it up. We were seeing, less pressure drop or less amount of puff and pressure drop when we actually were measuring some of the flow. And it was like clogging up the system physically. So, one thought is to just use an open-ended impinger, right? Those exist and that's an easy solution, but we did look into that and those just allow for really large bubbles to come through and they weren't dissolving in the liquid at all. You could just see smoke and vapor coming out into the smoke box. So we decided to try out some organic solvents in the first impinger to make sure that those oil droplets and whatever was clogging up here, nonpolar materials, were being able to actually dissolve and come out of the impinger itself. And so this is what the impinger looks like in figure C when we actually use an organic solvent in the first impinger. So we did a series of experiments where, again, we have two impingers. The first one is in line and then the second one after that. And we did different combinations of both the acidic aqueous in the impingers. There's some versions of metals collection use hydrogen peroxide. We investigated that a little bit, and then we looked at 3 different organic solvents in the first impinger, and then the second impinger we kept with aqueous to ensure that, in case the metals really needed that aqueous acidic chemistry to dissolve in the second one, then we would capture everything there. So all of the signal that we report for this is the combination of both impingers together. So here is the data for this 5 experiments. It's kind of a lot of bars, but let's just take a look first at the 2 aqueous ones, which are blue and yellow. So we definitely got some decent recovery. So I'll just show you the units on this axis here are part per million. And remember, our target concentration was 10 ppm. So in theory, if we were getting all of the metals in the oil to vaporize into the aerosol and collect them all, we would be up around 7.5 or 8 because that was our original spiking concentration. I'll show the percent recovery on the next slide actually in a different form. But this was just ppm here. And just to give a sense for, what we were able to collect. So ultimately, the one with the 2 aqueous impingers, really didn't have very good collection for a lot of these elements. The hydrogen peroxide was pretty good at collecting a couple of the metals, but some of these metals, we were more interested in a specific set of metals because we knew that that's what the cartridges were made out of. And so, not one solvent system was the best at every single one, but we decided ultimately to choose the acetone mixture. The acetone is the gray bars. We had sort of the best recovery sort of overall from the acetone aqueous mixture. And as I mentioned earlier on, so these bars are a combination of two samples. We actually have to analyze them separately in the ICP-MS and then add the signal together. So the organic impinger, so the acetone impinger was completely dried down. So there's just some residue left on the bottom. And then that was digested in the microwave and diluted to the final concentration and injected to the ICP-MS. The acidic aqueous impingers were just diluted to 2% acid. The original concentration in the impingers is, I think, around 5 or 8%. I don't remember exactly. And then injected directly into the ICP-MS. And then you add those two signals together to get these values. Let's see. Okay, so generally, we're not getting, if we're wanting these recoveries to be, around 7.5 or 8, which was our original spiking concentration, we're not really seeing that, right? So what's going on? We're trying to figure out like where our metals are going. And so we did an experiment where we looked at the metal, or sorry, the oil that was left in the cartridges after some vaping sessions. So this is a graph that's showing the oil before vaping, and this is essentially the spiked data. So we're seeing the same set of data as I showed you originally for our spiked recovery. This is, around 75%, 85% recovery. Here's that low number for mercury again. So these are the amounts of metals in the oil before they go into the cartridge. And then the lighter blue bar is then we vape that cartridge until it's, half full, maybe a third full. So we don't measure the aerosol or anything. We just vape it with our standard puff profile. And then we remove the remaining oil from that cartridge and look at the metals concentration. So in theory, if the metals weren't aerosolizing and they were staying back in the metal, we would see a higher concentration later on. And we do see a higher concentration for all the metals slightly, but not necessarily enough to account for none of the metals aerosolizing. So I think this is pointing to the fact that, and then additionally, there is an e-cigarette paper that is really similar to this, where they spiked e-cigarette liquid with 8 ppm and 80 ppm. And this is a quote from their paper. This is a CDC lab paper that says the metal transport efficiencies from their electronic nicotine delivery systems and to aerosol were generally quite low, and they only got 1 to 5% recovery. So there's something going on where even when there's metals in the oil liquid itself, you don't often see them manifest in the vapor later. So we'll touch on that a little bit more later on. We start to put this into context, but you will notice a very high number or level of nickel here and a much higher level of copper here. And some of these are, a little bit higher than just slightly increased. So what I think we're seeing here is some of the metals are staying behind, and we're not able to do like a full mass balance, unfortunately, at this moment. Okay, so just checking my notes here, making sure I'm not forgetting anything. This slide is showing, so if we're not able to collect all of the metals very well with oil and a vaporizer device, maybe it has something to do with the matrix or something else. So that's why we decided to spike some flour and just combust the flour and see if we're able to see the metals come out in that aerosol as well. So the main difference in setup here is highlighted down here below. We use a little glass pipe and put about 200 milligrams of flour here and use just a regular lighter. And it's one long continuous pull. So we don't puff, excuse me, we don't have a puff profile for this. So we don't lose most of it between puffs. So it's slightly different. And the other big difference here is we don't know the temperature difference between the two experiments, right? Generally, I think the combustion temperature is much higher than vaporizers. So there's some differences here that aren't perfect, but the data shows sort of similar. So let's walk through a couple of these here. We're seeing, so now this axis here is actually percent recovery from the spiked material. So this is normalized to, you know, this is a good example here. The mercury recovery here looks very high. Well, there's two reasons for that. One is mercury is sort of the most volatile of the metals, but also there was a very small amount of mercury in the original oil. So the recovery of this sort of looks a little bit higher. Arsenic is also sort of the next most volatile. And so we're seeing pretty decent recoveries actually in the aerosol for this. In the flour, you'll see there's a couple of them that are actually higher recovery from the flour, this cadmium and this lead. And so what that's kind of telling us here is there's potentially some matrix effects, but it is possible to detect these metals in aerosol. Maybe it's a temperature difference, maybe it's a matrix effect, we're not sure at this point, but we can get slightly higher recovery on some of these metals with a different matrix. Let's see. So moving on to analyzing the cartridge bits themselves. This is just a little kind of diagram of the cartridge. So as you know, there are hundreds of different kinds of cartridges out there. We can't investigate all of them for this kind of introductory study. So we stuck with one brand. Honestly, I don't remember off the top of my head. We ordered it online. And I almost feel like that's, I feel like it's representative of what people are using. And I'll talk a little bit more about cartridges in a couple of slides, but we did use the same brand and style of cartridges for all of our model matrix aerosol experiments. And so we decided to take it apart and analyze, you know, what elements are we seeing in these various parts. And we didn't just grind the whole thing up and analyze it as one giant sample. We took the parts apart and analyzed them separately. So this is when it's all put together here on the left, and in the right here is kind of all the different parts once we take it apart. And then here in this table are kind of the 5 different samples that we analyzed. And you'll notice that there's a couple of them that stand out, and I sort of highlighted them here, particularly in the heating coil. So the heating coil, so I hear a lot of people say, oh, well, my carts are fine, they're all ceramic. Well, that's not true. There is a metal-based heating coil somewhere deep in that device. And they are often coated with ceramic, and it's hard to see here, but that little white part that's inside the hole here is the ceramic, and the ceramic is the wick. It's the material that allows the oil to come into contact with the heating coil itself. So we separated out the heating coil, which was surrounded by this kind of ceramic cotton stuff. So we separated those into 2 separate samples. So we have the heating coil wire is mostly nickel and a little bit of chromium. And the heating coil ceramic had very little bit of copper in it. These are weight percents here in this table. The body metal itself, there's a couple different pieces that we included there, but obviously this metal part in the middle comes into contact with the oil while it's in the tank. There's a lot of copper in this one, and some lead as well, and a little bit of nickel. And then the rest of the pieces, you know, the mouthpiece, I don't necessarily imagine is going to be a big source because it doesn't get very hot. The glass, you know, as expected, is not a big source of these 10 metals. So I just kind of highlighted these 4 here, and so you can kind of keep those in mind as we see some other slides. All right, so we made a model matrix and we bought this one brand of cart, and that's we talk about some of the method development and things in the first paper. And some of the data that's moving forward is part of the first paper, but most of it is for the second paper. So we did go out and buy 6 commercial cartridges. We actually bought 7, but we ended up using 6 for the study. And I just want to give an overview of what we bought. So these were purchased from a Washington state cannabis retailer earlier this fall. They were all 1 gram size cartridges. We bought 3 from the same batch from each brand. So we had enough to do some experiments on. They were all, this is not a picture of the cartridges that we used in this corner, but it's kind of representative of, they were all more or less the same style, where they had 510 connectors, and these general like center posts with some sort of glass or plastic tank. The mouthpieces varied a little bit, but I don't think that that matters as much as like what the guts are made of. So they're unknown brands of cartridges. I was informed yesterday, you can kind of look closely at the bottom of them and find out. So I might try to figure that out. But the point of this is not to demonize any one brand at this moment. It's really just to get a sense for what's out there. All of them had strain-specific names and terpenes that were added. I don't know if they were from cannabis or botanically derived or what. And the viscosities, I'll talk about this a little bit more later, but the viscosities were visually thinner than our model matrix, just as a comment to keep in mind. And this table here is a summary of, so we blinded them A through F for brands. And these were the strains that were named on the labels. And the point of this is not to discuss differences between label claim and different lab testing, but we did run all of these for cannabinoid values. So this second column, oh, and they were used, different extraction methods were used as well. So these were all from the label listed. And so we did run these for cannabinoids here in this column, second from the right. And then this is the numbers that were on the label in the middle column. And I just want to point out a few things that were sort of funny or interesting. These 2 here had the exact same number of terpenes, and they detailed them out in the numbers. They detailed about 8 or 9 of the terpenes on the package, and they were the exact same values for terpenes between these 2 batches that were supposedly, one was live resin, one was cured resin. And if you'll notice the THC values, the label claim was indicating, there was some that were decarbed and some that wasn't. That's what you would expect with live resin. But when we ran it, it was 100% decarbed. The next one is this. When I was looking at the label, I don't feel like you often see this 2-to-1 ratio approximately. And when we ran it, it was almost exactly 1-to-1. This one here was a little bit of, the label said it had, all THC and a little bit of CBD, but we found that there was a lot of D8. So I don't know if that was intentional. They didn't advertise on the label that it was D8. They're not really allowed to do that, but at least in Washington. So I don't know if that was intentional, if they knew, if the lab that they used to test wasn't able to separate these 2 or what. That was a little bit interesting. And then this one here had a total cannabinoid number of 81, which was nowhere near, even when we added in the 0.5% of a couple other minor cannabinoids, was nowhere near that value. So, I mean, again, I don't want to like make the point of this talk label claim differences, but I just, kind of want to point it out. None of these were originally tested in our lab for the label. And so anyway, there's that. But the ultimate point here is that we bought 6 kind of random cartridges, random in the fact that they had to conform to some of these, they wanted 1 gram size, so we had enough. We wanted 510 connectors because of our battery, a few of those limitations. But I did try to get different types of concentrate, and we were able to get some different types there. Okay, so we used our acetone and aqueous impinger collection combination for all of these experiments. And there's kind of a lot going on here. But essentially what we did was, these are unspiked experiments, right? So these are just the commercial cartridges. and we collected the aerosol. And all of these bars are triplicate experiments. And you'll see how big these error bars are. I mean, sometimes they're bigger than the data point itself. And that's indicating how inconsistent these measurements are. And this is borne out in all kinds of other e-cigarette papers and other folks who've done aerosol chemistry experiments on cannabis as well. And there's just a lot of variability. So you really cannot take one experiment and say that your product is X, Y, or Z. So to talk about this data a little bit, this checkered bar is our model matrix. And you'll notice that, first of all, there's those 4 metals that we saw in the device itself are the ones that we're seeing at detectable levels. There's a little bit of manganese, but again, it seems like that's some background. And we didn't spend a ton of time trying to like figure that out necessarily. So you'll notice that, you know, there's a wide variety of some of these. Obviously, not all of these commercial cartridges were made with the same brand of cartridges. So who knows the metal concentration of the device itself. We are actually working on taking some of those apart, and so we can compare how closely they fall to the model one that we used, or are they all really similar? Are they all really different? But you'll also notice that our model matrix signals are pretty high for a couple of these as well. We noticed that too, obviously. And so we were like, well, did we make a bad model matrix? You know, what is the main difference here is, you know, the commercial cartridges all had some sort of terpenes added in. And we kind of intentionally didn't do that because we just wanted to keep it simple. So this was some of the data that we just added yesterday. So all of the gray bars are the exact same data from the previous slide, but what we did was we took our model matrix and added in 7% of some commercially available ChemDog. I chose ChemDog because we're chemists. And we added this commercially available mix into our matrix. And now we see numbers that are very, very much more similar to the commercial cartridges. So let's talk really briefly about a couple of things. First of all, the units on this y-axis are slightly different. The units here are, so I didn't want to calculate to ppm in oil because the oil that we were using for our model matrix didn't really have any metals in it. We don't know about the ones in the commercial cartridges, but you know, I felt it was disingenuous to back calculate to ppm in oil. So this unit is milligrams per cubic meter. This is a pretty standard volume measurement for regulatory purposes. So we'll get to some numbers comparisons at the very end. But obviously, there's something interesting going on when you have terpenes present and when you don't. And I was actually on a science kind of collaboration phone call with some other aerosol chemists earlier this week, and they mentioned independently of this, that they were seeing different signals when there's terpenes and when there isn't. So I'm not going to suggest that adding terpenes like reduces your metals exposure, but there's definitely something going on there. Is it viscosity? Is it the molecules themselves? I was hypothesizing last night with another science friend, is it just that the terpenes volatilize quicker because they're smaller molecular weight and the vaporization, the temperature cools down locally at the heating element and then prevents other metals from being aerosolized? Who knows, right? These are a lot of physical chemistry questions that I wish I had a team of grad students to answer, but unfortunately I don't. So I'm going to leave this here for now and move on, and we'll try to tie some of these together all near the end. Okay, so we also looked at these potentially metals from the cartridge device leaching into the oil. So this has been something that's gone around a little bit anecdotally in the cannabis space. In California, my understanding is in order to pass compliance testing, you actually have to submit filled cartridges, and then the lab removes the oil from those cartridges and tests it. So this graph here is showing, this is not aerosol data, this is directly measuring metals in the oil itself. So these are just the 6 commercial cartridges that we had. And we had the unvaped oil. So we open up one of the cartridges and just pull the oil out directly. And we're seeing measurable levels of nickel, copper, a little bit of chromium, again, some manganese. And then we vaped, so then a separate cartridge, we vaped, half the cartridge or so, and then took the oil out and tested that for metals. And you'll see now higher levels of some of these things that were in. The copper was making up the body part of the metal. And there's a lot of nickel in the heating element, and there's chromium in the heating element as well. And chromium in the heating element is only 1%, but you end up seeing chromium in a lot of different places. So this is a pretty decent indication that the act of applying heat itself will increase the amount of metals in that oil, independent of the aerosol, right? I do want to point out that these are the same, these highlighted in red here are the 4 that we kind of saw in high concentrations in the hardware. But if you're in California and you pull that oil out of the cartridges and test for the big 4, you're not going to see anything. That's going to pass. So just some pointers when we're thinking about, regulating these kinds of compounds in cannabis, we might be looking at the wrong compounds. So I'm happy to chat about that with interested policy folks. Okay, so we also tried to compare a non-cartridge way of aerosolizing cannabis. So we tried a dab rig. So this is an image of our dab rig. We intentionally chose an e-nail version where the heating device coil is outside of the quartz, we'll call this sample container. There's nothing I love more than buying drug paraphernalia for my job. And so it was pretty fun being in the glass shop, looking at different dab rigs and explaining to them my requirements. It has to be easy to clean. It has to be, no color, all of these things. So this is just our setup, and this is the tube then that goes directly into the impingers. And so we heated this electronic nail to 380 Celsius. We picked that because it was kind of in the middle of our e-nail settings. And we used a metal tipped syringe to apply about 200 and 250 milligrams of oil once it was heated. And again, we did one long continuous pull for this, because if we puffed it and waited, then most of it would just go up the fume hood. And again, the impingers were the acetone and acidic aqueous combination. So what we're looking at here are vapor collections, and this unit here we just calculated to micrograms of metal per smoking session. So we don't have the exact same volume here because of the one long continuous pull versus our puffing with the cartridges. So this is just a straight measure of micrograms of metal here on the y-axis. And you'll see the cartridge has much higher signals for the nickel and the chromium. The dab rig does have some small signals for nickel and copper. We didn't analyze this metal. We didn't analyze the quartz glass part, but I think it's sufficient to say that the 2 elements that we see in the heating coil are definitely much more present in the cartridge samples than the dab samples. We did not do a ton of replicates with the dabbing, but I think this was really more to just highlight the source of some of these metals. All right, and then we just removed the oil altogether. And this is also brand new data from earlier this week. We've run a number of what we call cold blanks, and we do subtract all of those from our final data. But here we finally ran some what we're called hot blanks. So this is just the cartridge with no oil in it attached to the battery run through this standard 50 puff profile. So there's not even any oil or matrix effects here. And the cold blank, so again, this is milligrams per cubic meter, not ppm or anything, because there's no mass really of sample to back calculate ppm into. So you can see here in the hot blank, a lot of nickel, a lot of chromium, and some copper as well. And so these were the main components of the cartridge device. Seeing a little bit of lead here as well. So this is pretty indicative that these metals are coming off the devices when they're heated, full stop. This is a comparison study. I'm just doing a time check here. Oh, we're running short on time. Comparison study, but we're almost done, of some e-cigarette work. And they looked at 3 different aspects of e-cigarettes and e-cigarette liquids. We have this yellow part is what they call the dispenser. It's really the liquid before it goes in the device itself. So just out of the jar that you buy it in. And then they tested the aerosol in the gray, and then the liquid that was left in the tank after it was smoked or vaped. And you'll see that if you look between the red and the yellow, there's definitely more of these metals after the smoking than before the smoking in the liquid itself. And this paper was really dense, and I don't fully understand how this is a ppm unit of aerosol, and this is also a log scale here. And their error bars are really, really huge. This paper had an N of about 56, which is why they're using box plots and whisker plots for this. But this kind of made us feel a little bit better in that they have very large error bars, meaning sometimes you get huge signal, sometimes you get very little signal. It's really inconsistent kind of between experiments. All right, so to put some of these numbers into a little bit of context, first I want to focus on the left-hand side here. We have the CDC ATSDR, which is the Agency for Toxic Substances and Disease Registry. These are MRLs, which are minimum, what do we have here? Minimum risk levels, and they're estimates based on a number of different aspects. And so these aren't necessarily toxicologically based or anything, but these are the values that they have listed for these sets of metals. They don't have values listed for all the metals that we investigated, but they're pretty low. And so these are the meg per cubic meter unit. And if you want to look at that on a graph, the dark bars are our signal for these metals, and the basically non-existent bars are these CDC levels here. This copper is actually an oral safety recommendation, not an inhalation. So the inhalation numbers are usually an order of magnitude lower or so. So if you were looking at these values, we're failing if you're looking at the aerosol. If you look over here on the right with the FDA, and the PDEs are the maximum daily exposure for elemental impurities in pharmaceuticals. So, and these, again, they didn't have all the metals that we investigated, but if you were, say, to test the aerosol, our values and compare them to these limits here, the yellow numbers are, you might fail, you might not, given the fact that we have really large error bars. If you had a high signal for that experiment, you would fail. If you had a low signal, you might pass. For the copper and the tin, it seems that we are relatively safe. Again, these are estimates based on impurities for pharmaceuticals. This is not necessarily, an OSHA or an exposure guideline. So I just kind of wanted to, there's a lot of numbers and a lot of units that we talked about. And so here's some comparison to some other numbers as well. I think the thing to keep in mind is you really shouldn't be inhaling metals full stop. Our lungs are designed to inhale pure clean air and not a lot else. So a really brief overview of some of the logistical complications of this. I get a lot of people asking, like, why didn't you do this? Why didn't you do that? It's a lot more complicated than you think it might be, just at first glance. It's basically impossible to test the oil and the vapor from the same cartridge because they're hard to get open. There's not much oil left in the cartridge. And so you have to, like, the aerosol experiments and the oil experiments are from different individual cartridges. The spiking part is difficult. The tubing, you losing condensate. I didn't mention this, but there's a lot of rinsing of the tubing that's important in our sample collection as well. It's very difficult / impossible for us to measure the temperature at the actual, site of vaporization. So we don't know what actually the voltage or temperature is at that site. The batteries themselves are highly inconsistent, given the fact that there's all kinds of different batteries. Many of them are very cheap, disposable. Even the quote unquote expensive battery that we bought was very, very, very unstable between different puffs. So we had to leave it plugged into the wall. Formulations that are in the cartridges, we don't know what's in that stuff. There's a huge amount of variety of cartridges and batteries types. And also just quantitative capture of vapors and analysis is really hard. It's time consuming. It takes almost a full day to get 3 data points, at least with our current setup. So there's a lot of logistics here that make this time consuming and expensive and difficult. So to summarize and wrap things up here, that we're short on time, we basically demonstrated that, we can spike aqueous metals into nonpolar concentrates. We updated some of the collection methods, most notably adding a nonpolar solvent as one of the impingers, and also rinsing a lot of the tubing to make sure we're collecting. If we didn't rinse and add all of that rinsate to the ultimate sample, the signals were much, much lower. We analyzed the cartridge components themselves. We analyzed some vapor from cartridges, both our model matrix and commercial. We compared some of that to flower combustion and dab data. And basically, I think we can safely say that the metals we're seeing are coming from the device itself, and they are outside of the big 4 that are generally regulated. And a lot of this data agrees with some of the e-cigarette work. I didn't have time to go over all of that historical work very much. So obviously there's a ton of possibilities for future work. We'll be able to do some of this ourselves, but not all of it. All the different types of cartridges, all the different types of temperature and voltage levels, different types of matrices, better characterization of the aerosol mixture itself, obviously other compounds that you might not need to do so much aqueous nonpolar, justification. The pesticides and VOCs are, a lot of nonpolar basic analysis. So there's a lot of different directions we can go. There's a lot of things that, this is not a perfect set of experiments, but we think it's pretty important to get this out there and hopefully it's useful to the industry. So I'm going to wrap it up there. I don't know if we have time for questions.
Yeah, thank you, Amber. That was such a great presentation and a lot of stuff there. So yeah, Amber, do you have a little 5-10 minutes to stick with us?
Yeah.
We do have some audience questions.
Yeah.
Awesome. And yeah, so far we've had 0 attendees drop after the hour, so it sounds like everyone wants to sounds like everyone wants to hear you answer some of these. So okay, first question comes from Toby Astill, and he's asking, are you fully digesting the metal pieces of the vape assembly to determine metal concentration?
Yes, to my knowledge, the metal parts are not difficult to fully, so some of that picture, they weren't all really ground up very well, but we were able to fully dissolve the metal parts. The glass, not so much, but some of it definitely dissolved, and that was not really the focus of the issue either. You have to get HF in to dissolve glass, and it gets complicated.
But so you're saying you did fully dissolve or digest the metal?
Yeah.
Cool. Okay, next question from Sarah Lundfelt. She's asking, do you think the different percentages of cannabinoids in the commercial cartridges have any effect on the metal leaching?
Potentially, yes. We really don't know. I think there's a lot of interesting matrix things that could be looked at here. And given all the variables, we kind of had to just pick a few variables to look at and stick with that. But it's a definite possibility that the molecular components of the oil itself have something to do with metals leaching for sure.
Yeah, Amber, I think even just sitting here kind of reflecting rapidly about your presentation, there's so many other things to investigate as you mentioned, so no shortage there. And a related question to Sarah's question from another audience member, have you looked at MCT oil in a similar way to terpenes to see how they affect metal vapor? How they affect, I think it's supposed to be metals in vapor.
Right. No, we didn't look at any other cutting agents. Washington State theoretically requires people to list on the label if they put anything that's not cannabis in their cartridges. And I mean, I don't look at every label that's out there, but according to the labels I've seen, no one adds anything that isn't cannabis in Washington. It would be interesting to look at some thinning agents, and that's a natural progression of this set of experiments, but we have not.
I think we could spend a whole session talking about the nuance of what you just said about the regulation.
Yeah, there's a
The
lot
little
to unpack there.
yeah. I'm trying to not talk about it for the sake of time right now. So, and to remain topical. So, a couple more questions. Back to Sarah, she had another one is asking, have you looked at how quickly metals leach during vaping? 5 puffs, 25 puffs, etc.?
You mean into the oil? Well, I'm not sure if it's into the oil. We did
Yeah, I
not
think
investigate that.
yeah.
We basically just wanted to make sure that there was some heat applied and that there was some oil left over that we could analyze in the cartridge.
Mhm.
I definitely don't suggest, if you vape cartridges, to ever smoke the last bit of it. I think some of the high signal, I didn't get a chance to talk about this during the talk, but some of our suspicions about viscosity were potentially our thicker mixture was maybe not wicking fast enough into the heating element, and maybe some of the puffs were just hot blanks, like hot air coming off of the heating device or the heating element itself. So that might have something to do with the viscosity. Charlie, the technician who did a lot of these, that's partly why he implemented that 10-minute rest between the puff sessions, was to allow the oil to make sure that it was seeping into the wick appropriately.
I think anyone who's tried a vape cart will identify with everything you're saying. The viscosity issue, the dry hit issue, and there's also this thing about the reheating. I mean, the first hit off even like a high-end vape cart, a live resin vape cart, doesn't taste the same as the middle hit or the last hit, I think. So
And I also think a lot of that has to do with the inconsistency of the batteries, and the heating is different puff to
oh,
puff.
yeah, it's absolutely wild. And what you were saying about the battery itself too, it's also just rife. I mean, a lot of cheap hardware out there. So, anyways, more questions coming in, and this always happens. The questions start flowing, and then we just get like a flood. So let's try to squeeze in a couple more here in the next just few minutes before we call it for today. So, next question: what serial dilution would be needed after digestion to run your ICP-MS? What are some of the issues
So
you've or yeah, sorry, go ahead with that one.
Right. So I don't know the exact number off the top of my head. I don't know if Charlie or Srini want to type it in the chat, but I know that we diluted to 2% acid concentration when we inject it into the machine. So I think it ends up being about 40x dilution, but I could be wrong there. But the final
Okay.
acid concentration is 2%. And we originally had higher acid concentration and it was messing up our instrument. So we had to adjust and dilute further.
And just wanted to remind the audience, Amber does have her email up here on the screen, so if you want to follow up with her,
Absolutely.
please do. Yeah, please do reach out. So, there was another question from same audience member. What are some of the issues you found, or sorry, I'm trying to read this. What are some of the issues you're finding for equipment to collect the smoke? Were there plenty of options to purchase the puffer? Is what the question says.
No. There are a couple of companies. These smoke machines there's a couple companies that manufacture them for cigarette analysis. A lot of developed countries have cigarette smoking testing requirements, and these machines are standardized for that. So there's a number of options. They are crazy expensive. I mean, this machine, which does very little, costs more than my car. I don't have a fancy car, but still. So there, if you're looking to do this kind of work, there, I think, are potentials to develop your own puff machine. But if you look deep into the Caresta and ISO methods, there's a lot of parameters about like pressure drop at the beginning and end of puff sessions, and the differentials between puff cycles and things that you might not be able to control, but it kind of depends on how specific you want your data to be.
And we'll call this the last question because it plugs into that. Someone is asking in the same vein about parameters for the puff machine. They're asking what were the parameters for vapor collection, pressure, length of puff, temperature, and are there some standards in the industry like what you're referencing for tobacco companies or e-cigs? Um,
Yes, I didn't spend too much time talking about those, but we did have, so in terms of the puff profile, we didn't measure the pressure drop every experiment, partly because I didn't want the flow meter to get really gummed up with cannabis on the inside of it. But we did measure pressure a handful of different times at different places in the flow line, just to make sure that it was puffing the way we thought it was. And part of the reason we had to use the organic solvent was the aqueous impingers were literally getting so clogged that we weren't getting any real puff action at the other end. So I'm happy to answer specifics about those settings via email if that's easier. But we tried to keep it as close to Caresta standard method as possible. But we didn't do a lot of specific characterization about the actual puff profile. But we did do some checks on volume and flow and that kind of thing.
Awesome. Thank you for sharing. So we are at about 15 minutes over, so we'll have to call it for today. But Amber, thank you so much for coming and sharing your research, your experience, your knowledge with us.
Yeah,
We'd
absolutely. One really fast thing at the end I didn't get a chance to mention that kind of wraps it up is, if you're not aware, Colorado is proposing aerosol testing for inhalable cannabis products. And so if you're someone who's involved in those rules settings, we would love to be a resource for you in this process. So reach out.
Awesome. Well, anyways, thank you everyone for attending. Reach out to Amber at her email here on the screen with any other questions, and we'll see you all at next month's Journal Club.
Thanks, everybody.
Thank you, Amber. Bye, everybody.